that of the science of astronomy and, you know, science in general. So hope everybody's doing well out there. I think I just tweeted. Yeah. Okay. Wow. I'm on top of things tonight. Can't believe it. Can't believe it. All right. So yeah, hope everybody's doing well. Now, if you're new to this live stream and are either watching it live or watching it later, hey there, Tom. Um, this is just a casual, fun get together of friends every day, practically every day. Um, uh, yeah. Um, Once in a while, I get into a situation where I'm not going to be able to be here at 2 hours UTC, and instead of having to reschedule things and or having to hurry and rush and everything else, I just you know kill it that day. Hey there, Bobby. Nice to see you. Um, so yeah, this is just a fun, casual get together of friends. It's a circle of friends. It's like a virtual porch with our lounge chairs. We're sitting out. The sky is starting to get dark, right, and the stars are starting to pop out, and we're sitting there with our consumable of choice. So cheers. This is the hydrogen hydroxide again. So cheers. Uncle Bill with the blue wrench painting everything yellow in the chat. Hey, hey, hey. Nice to see you, Uncle Bill. Hope everything's going well in your world and in all of you's worlds. Yeah, things are good here. Things are actually kind of interesting. So I hope to talk a little bit more about that sometime soon. But yeah, I'm hoping this weekend to get um, some research work done to try to understand my the results that I'm getting from measuring these binary stars and trying to understand why the accuracy of um, my measurements are so inconsistent. So I'm trying to understand that. I found a bug in my code in the software that I'm using to um, do the analysis of this data. So, it's driving me insane, and that's how bugs go. I mean, if you're a programmer, hey, oh no, I think I'm about to kill. Okay, look, I'm gonna kill that screen. Oh man, I always leave the live stream going on my Linux machine, and I haven't learned yet to turn that sucker off because it just messes everything up. Now, luckily, tonight it just sort of crashed, right? The browser just sort of crashed, so I'm just going to have to uh, -d 0.1, and then I'm going to do a capital M. All right, it looks like it's already off, so I can restart my browser, restart the browser. Anyway, I don't remember what I was talking about. Oh yeah, the project. Um, so yeah, uh, I'm seeing consistent data, but it's not accurate. So yeah, it's just driving me insane. I'm gonna try to work on that this weekend if I can. Let's see, can I do that? I think I can. I think I can. I think I can. Let's go over here and make sure that this is nowhere to be seen. Go whammo like that. All right. So yeah, that's sort of what I'm going to be maybe messing with this weekend a little bit. Um, uh, yeah, we'll see. I guess we'll sort of see what else is on the menu for at least the weekend here. But so consider ourselves on, like a virtual porch with our actual consumables here, and sun is setting. It's getting darker, but the temperature's just right, right, and maybe there's a little bit of a breeze. Maybe it just feels really, really nice, right? So we're sitting out there, and here we are, right? Here we are, just sitting around chit chatting about all things astronomical, all things science. So that's another aspect of this live stream is that yes, absolutely. We're having loads and loads of fun. This is very, very cool. Um, but we're also a little serious, right? A little. Um, it's not just sort of irresponsible fun. It's pretty intense fun, right? And so yeah, around here we can be skeptical um, uh, about things, but also try to remain open-minded if you can. That's oftentimes really, really hard, because we sort of get set in certain thoughts or certain um, beliefs, and it's naturally difficult to shake those. That's no problem at all. Just try to be as open as you can to things that you hear about, and see, and think of the possibilities. Think of what else um, could be happening uh, with things, and what what things don't we know, and even more important, um, what things don't we know that we don't know. so those are impossible, I guess, to know, um, unless something happens and makes them obvious, right? So yeah, let me start up I think the chat is still going. Is the chat still going? I don't know. It looks like is it it's going. I'm gonna test it. Looks like I can see it at least. All right. So yeah, that's what this is all about, and it isn't about necessarily me sort of getting up on a pedestal as like one of the high priests, and you ask me things, and wait for my answer, and my answer is uh, uh, how things are. It's like no, no. It's all I can really do is sort of relay uh, what things I have I have learned, things that I so-called know, and yeah, remain really curious and in awe. Right. That's all I can really do. So let's see, where do we want to go from here? Cheers. So having said all of that, the, the topics are, there's a lot of different things that we can be talking about. And in this live stream, I am personally open to anything, right? From you know any of the beginner stuff to the intermediate stuff. I'm just seeing sunset here. Looks looks pretty good again. It's still pretty red. Still pretty red. There's still a little bit of smoke in the air. Um, so beginner basic things. you know, what to look for in terms of getting a telescope, say, how to learn the sky, you know, just, I mean, even the most basic things like, you know, what's a star, what's a planet, what's a moon, uh, um, you know, what are atoms, what, you know, all of those, you know, and I can't really say basic because you know, that's incorrect terminology, um, because everything is extremely complicated, right? So there's nothing really basic uh, at all. But yeah, you know, sort of the fundamentals, right? You know, the things that in order to sort of get into astronomy, you sort of need to start learning about, right? Time is a big thing, right? That's why on this live stream, right, I will always say that this live stream starts at 2 hours UTC, right? Um, and the reason why I don't go through, you know, the list of 5 or 6 or 10, well, you know, that's this time Eastern time, this that time Europe, blah 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 blah, isn't that I can't. I mean, come on, anybody can do that. It's just subtraction. You know, there's nothing to that. Um, at all. But the idea is that, you know, one, if you want to get into astronomy, one of the fundamental building blocks of astronomy and science in general is having a relatively good grasp of how we measure time and how we sort of perceive time, right, as duration. You know, things last a certain um, duration, and you know, we chop that up into pieces and call it, you know, seconds and minutes and hours and milliseconds and nanoseconds and decades and centuries and millennia and you know, on, right? um, so you know, uh, when I only give a single time for this live stream, well, it's because there is this live stream does only occur at one time, and that's right now. That's it, right? Um, but you know, uh, we have to, you know, uh, because of how things are, right? Um, all of our now is at this moment, right? And we're experiencing that simultaneously, right? But according to another means of measuring things, right? My time, I mean, the sun has just set here, right? Now, where you are, the sun is either still up or it's already down, right? It's not just set, right? That's for my location on this sphere, right? So so yeah, uh, so when I say that this live stream starts at 2 hours UTC, that's 2 hours at a particular location on this planet. That happens to be a place called the prime meridian, and that goes through, of course, a longitude of 0 degrees, right? And that just so happens to pass through Greenwich, England, and down through Western Africa, and then down into the southeastern Atlantic, right? And it connects the two poles, right? So there's an imaginary line that goes from the North Pole down this longitudinal line down from a latitude of plus 90 degrees to the equator, which is at 0 degrees, and then down to the southern pole, which is arbitrarily set at negative 90 degrees. Um, so that line we've decided is our universal now, right? our universal time. And so depending on where you are then on that sphere, your relative time to that will be different, right? So here, where I am, I'm in southeastern Arizona in the United States, where it's dark and quiet. um, I I live in one of the states, one of the few states, and I think actually one of the few places on this planet that does not observe daylight savings time. So I am constantly on Mountain Standard Time. Mountain Standard Time. And Mountain Standard Time is always 7 hours behind UTC, Coordinated Universal Time. And so 2 hours UTC in 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 that time domain is actually 7 p.m. My local time, right? So I'm actually, and it's 7 p.m. the day before, right? So right now, right, it's 2:17 UTC on June 9th, but where I am, uh, sitting right here, it's 7:17 p.m. on June 8th. So um, hello to all of those in the future, and hello to all of those in the past. But really, there is none, right? The only thing that we've got is right now, and that's universal, right? Everything is happening right now, and uh, things that are going to happen in the future will probably definitely happen. Yeah, and things that have happened in the past most definitely have happened. Um, and that's it, right? So all these other ideas um, are sort of relative measurements. And so these are some of the concepts that you just sort of have to wrap your head around in order to get into astronomy. And time is one of those building block foundational things that you know if nobody understands time, right? Nobody understands time. It just sort of is, right? Um, uh, but so don't worry about that. What you got to worry about? Hey there, Gilles. What you got to worry about is um, measuring time. The myriad of ways that we humans measure time. Um, and so if you can become familiar with that, then you're well on your way um, to getting into astronomy and having exercised your brain a little bit will actually help you understand lots of other things. Um, uh, because you start to think like an astronomer. And once you start to think like an astronomer, then lots of things just sort of lock into place. It's like, oh yeah, yeah. So cheers. All right, well, cool. I think let's see see uh, this is actually one of those nights that I can't really I I wasn't able to really decide on um, uh, what to pull out of my back pocket if need be, and but I guess maybe where we can start is that Tom had posted a article that he found, um, and I'm gonna get it here. I'm gonna go over to my Discord server, and if you haven't gotten onto that yet, I will post an invite for you right now. Uncle Bill, I'm going to do it. Can you believe it? I'm going to do it all by myself. let me get over here. Doing two things at once. I'm loading Discord over on my laptop, and I'm loading Discord. Let's see. Invite people. Send the invite link. Let's see if I can do that. Oh. Oh. I'm going to do it anyway. There's another one. We both did it. All right. Well, anyway, let's go over to my Discord server. Uncle Bill, you're too fast and too good. I'm going to share my screen. I know. You keep up the good work. Hide. We'll come over here. All right. Well, let's look at the. Yeah, so Tom, I'm looking at your response in the Discord channel here, and let me start up my live stream over here on my smartphone too. So, okay, so yeah, I looked at the paper a little bit too today, and yeah, I've maybe we'll get into this a little bit, but let's look at the sky and tell since you're sort of recommending that here, and let's see what they have to say. So, a massive neutron star with a two-faced companion. Yeah, this was sort of like a double discovery, which it's like, well, hey, that's all right. Oh, okay, all right. Well, Uncle Bill's is better then, right? Because it lasts longer. I'm gonna have to figure that one out, Uncle Bill, so I can do that too. You're gonna have to tutor me on that. I'll look first. If I if I can't find it, I'll ask you. So yeah, neutron stars. Just as a very 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 brief primer on those. So as the story goes, right? As the story goes, a neutron star is one of the possible end states of a star, right? Once a star has evolved and sort of gone through its life, this is one possible uh, state that it'll sort of end up as. It's, I guess, one of the one of the three or four different kinds of dead stars, right? Um, and the 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 fates of stars, at least according to the current story, the fate of all stars is determined by their mass, how much stuff they have, and usually it's how much mass they have when they're newly born, newly made, right? That seems to, at least according to all the models and everything else, that seems to dictate how stars will evolve, right? Um, and so, in order to become a neutron star, a, a star has to be pretty massive. It has to be, again, at least according to the current story and all the models and everything, a star that is about 1.4 times the mass of our sun, or greater, right? Up to maybe 4 or 5 solar masses. Maybe not that many. Maybe about 3. Yeah, maybe about 3-ish or so. Um, those stars will become the so-called neutron stars. And the idea here is that if you take like a 2 solar mass star, right? Um, once once the the hydrogen fusion, which supposedly is going on in the centers of these stars, once that starts to slow down, right, that's sort of providing outward pressure, right, to hold the star up. Well, once that starts to die down a little bit, you've got all that stuff, right? And all that stuff wants to collapse. It wants to fall down, right? It wants to go in. Um, and so it does that, right? And the star shrinks a little bit until heavier elements can start fusing. And at that point, lots of things can happen. Usually the star will go into what's called a red giant phase, where it actually expands, because that fusion of those heavier elements um, produces a lot more pressure, right? So the sun can expand out, to be a red giant, say. But then, after that sort of fuel is used up, um, then the star begins to collapse again, and a number of things can happen at this point. These 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 sort of expansions and contractions can go on for a little time or so, and I think in the case of neutron stars, that happens. That happens at least a few times, right? Because it'll go through, depending on its mass, again, how much stuff is actually there. It can go through helium fusion, then it can go through carbon fusion, um, and I think there's one more until it gets to a fusion state where it's producing iron. And it turns out that if you try to fuse iron, that actually takes more energy to fuse than what you're going to get out of it through that process. So that process will stop at that point. And because there's still so much stuff, right, the star begins to collapse. And that collapse, um, uh, let's see, the best, well, what's happening, right, is that the that collapse is so uh, enormous. Um, the amount of gravity, that gravitational force is so much um, that the actual, I'm sure you've heard, that there's like this enormous amount of space between the electrons in an atom and the nucleus, right? There's this huge amount of space, right? Well, as the theory goes, this gravitational squeeze is so enormous that it will actually squeeze the electrons and push them down into the nucleus, right? Into the nucleus, where they then combine with the protons to form neutrons, right? So it's as if you've taken all the space out of the atom, right? So something, 2 times the mass of our sun, all of a sudden is a couple of kilometers in size. So it really, I mean, you've heard, right, that there's not that atoms are 99.9% empty space. Well, this the this is sort of uh, um, showing that, right, that you can have the amount of material that takes up a star that's, say, twice as big as our sun, and squeeze it down to the size of a city, right? So that's pretty impressive. If that's actually happening, I don't know, right? That these kinds of scenarios, right, are 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 fundamentally based on models, right? Now we've made lots of observations, and we've put that information into these models, right? But these models make some basic assumptions, right? I don't know, but that's sort of the story, right? That that's sort of the story. So sorry, that's sort of a long-winded story, but what you end up with is this object that is supposedly primarily made of neutrons. So they call it a neutron star. Phew. Um, Most neutron stars rotate in some way because the collapses that that actually occur. Well, one, the most stars, I think, I dare say all stars have some form of rotation, right? Some kind of rotation. Our sun does, right? I mean, our sun. Um, well, it sort of depends on where you look on the sun, but it has between a 25 and 29 Earth day um, rotation period or so. So every few weeks, 4 weeks or so, about every month or so, um, the sun will make one rotation, right? Well, now, just like a skater, right? If they put their arms out and rotate, they sort of, turn at a certain speed. And as they pull their arms in, they increase their speed. That's called conservation of angular momentum. And so if these stars are rotating when they start to collapse into a neutron star, it's just like the ice skater pulling their arms in. And so this object, this neutron star, tends to spin pretty fast. And some of these things, and this is another red flag for me. There, inside of astronomy and inside of science itself, there's a lot of red flags, okay? And this is one of them. And that is these millisecond pulsars, right? So a rotating neutron star um, that we can that we can see rotating is what's called a pulsar. The idea is that, along with having a lot of mass um, in a very, very small space, um, these objects also have very, very strong magnetic fields, supposedly, right? Um, and so if there's any kind of material or anything else, that material will sort of get concentrated at the poles of these rotating um, neutron stars. And energetic material tends to emit light. So as these pulsars are rotating around, or these neutron stars are rotating around, um, if we can see those beams that are sort of coming off of the poles, then we'll actually see this star blinking, right? And funny thing, I mean, not so funny, pretty logical that when they first discovered these pulsars and realized how regular they were, right? They're like extremely precision clocks, ding ding ding, just really precise. They thought for a while that they had found intelligent life, right? And that's very, I mean, that's a logical um, um, conclusion, to come to. It's like, holy shit, we found them, right? I mean, look at these signals. I mean, that they're so regular that nothing in nature could be that regular, right? Because everything around us is, there is some order, but we see chaotic systems everywhere. We don't see, these regular pulse things. So it's like, wow, I mean, jumping to conclusions a little bit, but it's like, wow, that's pretty amazing. And later on, we uh, identified these objects in the sky, and it's like, oh, okay. And then, of course, the investigation was on to figure out what the hell they were, right? Anyway, so they found um, uh, they found a neutron star that is being orbited by uh, sort of a less massive um, star. I think in the paper it said that it was about a third of a solar mass or so. Now the interesting thing is, um, okay, okay, I sort of read that wrong. All right, 2.01. So up until now, right, the most massive neutron star that they had found was about 2.01 solar masses. Um, so yeah, as I said, this is a millisecond pulsar. Okay, so we can look in the paper to see exactly what it is, but this star, right, this so-called neutron star, that's the size of a of a city, right, a few kilometers across, maybe, um, is spinning thousands of times per second, or at least hundreds of times per second, right? But if it's a millisecond pulsar, then that can be, there's sort of a range there. But let's just say, that it's a millisecond, right? That means that this object is spinning 1,000 times a second, right? Now, just, close your eyes and imagine a just a sphere, right? A sphere the size of your favorite city rotating 1,000 times a second. That's, I mean, it's really kind of interesting to imagine, but for me, I don't know. That sort of throws up a red flag. It's like, I don't know. I don't know. That just seems a little weird. I don't know. Just seems a little weird. I mean, it's amazing, right? But it's just a little weird. I don't know if things are that weird, and I'm just wondering if there's another explanation for those pulses. I don't know. So, well, and the other thing, of course, is that this pulsar has a companion, right? That goes around it once every 4.14 hours, right? 4.14 hours. So now, right, imagine for a moment a uh, a star smaller than our sun, right? A third of the mass of our sun. I think that's what the paper said. A third of the mass of the sun. Um, let's see. Let's let's go to the paper while we're doing this. So imagine a third of the mass of the sun orbiting this neutron star that is spinning at 1,000 times a second. Okay, star. This third of a solar mass, sort of regular old star, is careening around this pulsar and going around it once every 4 hours. Oh, look at that. I think they're carrying out maintenance on the 9th of June at 2 hours BST. 2 hours BST, is that 1 hour ahead of UTC? Am I reading that right? I think so. I said this was easy, right? But I don't know what BST is. I think BST is 1 hour in front of US UTC. Is that correct? Can anybody help me on that one? So I don't know if I'm going to be able to grab this article or not. Oh, I can. Yeah, it's there. So yeah, I try to imagine these things, and sometimes what I imagine just sort of bothers me a little bit. Yeah, British summertime, so +1. Yeah, thank you, Uncle Bill. Um, so yeah, I don't know, right? I mean, EO orbits Jupiter every like 16 hours or so. Um, that's that, and EO's moving pretty fast, right? So I don't know. It's just things like this sort of bother me a little bit. So here's the actual paper. Oh, let's see if let's see if Sky and Tel has anything else here. Whoop, did I there it is. So yeah, what they did through some clever modeling, right? So they looked at the spectra of this system and found some interesting things. And through some kind of model, I definitely cannot claim to really understand their model. I mean, trying to understand the these things definitely takes more than a couple hours to do. So, I mean, these people, they work on them for months or years, right? I think this data, right? This data, um, let's look. I think I saw, yeah, okay. Look, this data is almost 4 years old. So they've been looking at this data for a long time, right? Either that or it's, been sitting around all that time, but I doubt it. I doubt it. My guess is that they've been banging on this thing for this whole time, because that's what it takes. That's what it takes to figure these things out, right? So yeah, they had a pretty good run here, right? Pretty good. So yeah, that's pretty much it. They collected lots and lots of data, right? Lots and lots of data. Um, but I was looking at these spectra, and they're using the, if I remember right, they're using the hydrogen lines, the hydrogen Balmer lines, as they're called. The Balmer lines, the Balmer series of hydrogen, those occur in the visible wavelengths, right? So you've got hydrogen alpha, which is way out here, out to the right at like 6,800 and some angstroms. There's H beta, right? Here's H gamma, here's H delta, it goes all the way down, right? And this is just representing the electrons in these hydrogen atoms are changing um, energy levels, and those energy levels are quantized, right? That's 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 the whole idea. Um, and but since there's a lot of hydrogen atoms all doing different things, we see these lines at all the different wavelengths. Now, just as an aside, just, and you're not going to be able to appreciate it here, but I just wanted to point out the fact that my favorite color in the whole spectrum is H beta. And here they're calling it 4861 angstroms. I've always known it to be 4868. So maybe there's a little bit of debate there about what wavelength H beta actually is. But if you ever get a chance to see light in H beta, right, 4860-ish angstroms, remember that is cosmic's favorite color, and it is. It's absolutely fantastic. My favorite color of all time. Um, but what they've done, right, is they've done some kind of comparison between the hydrogen lines and these magnesium lines here, right? These magnesium lines. And what they've done is they've taken some spectra of sort of some known spectral type stars, like a G5 star and an A5 star. And these are the spectral lines that you get when you're looking at a G5. So now our sun is a G2. So that's pretty close to a G5. So the spectrum of our sun would look, similar to this, right? And so then here's the spectrum of the pulsar and its companion at an orbital phase of 0. So that's probably when the companion is either going in front of this neutron star or going behind it. I'm not exactly sure. And then they also do a spectrum of it when it's half an orbit past that. So yeah, I'm sort of thinking well, as you can see, there's quite a difference in the spectra, right, between when you look at it in this orbital phase and this orbital phase. And so the theory is that this is a lot cooler than this. And since there's, I guess, also an assumption that the companion is tidally locked to the pulsar in some way, right? So it's always, one face is always towards the pulsar. I guess the idea is that one side they're thinking is hotter than the other by a pretty significant amount, like 3 3,000 degrees or so, something like that. So here's their model, and I'm not gonna I'm not gonna get into the model. Here they're showing the phase up here. That's kind of cute. Yeah, so let's see, can we? Okay, all right. So yeah, they've actually run this through a series of models. Hate that. So they've run it through a series of models to sort of get some numbers, and then you can compare them to what the data actually shows. That's kind of cool. But as you can see here, so they're coming up with a pulsar mass of 2.27 times the mass of the sun, and the companion mass is about a third of the mass of the sun. And let's see, I'm not quite sure if I know how to read these temperature things down here. But I guess the basic idea, right, is that the companion galaxy they're measuring to be about, 5,500 degrees Kelvin, and the temperature. I don't know. I guess this is the temperature of one side and the other, right? Yeah. So, so the temperature on one side is lower than on the other side. That's kind of cool. The neutron star, supposedly, I guess, is like heating up that one side. I'm not going to try to. I'm not going to try to get into the models at all. Physical model fits simultaneously the Balmer and magnesium 1 lines. Okay. So, but I guess, yeah, going back up to the spectra here, one thing that sort of bothers me a little bit is, and yeah, they're sort of claiming here are the magnesium lines, these things here, right? Let's zoom in a little bit more. Can really. So here are the magnesium lines, and supposedly, I guess it's a triplet, right? It's supposed to be a triplet. So there's actually supposed to be 3 lines in there. Yeah, I don't know, Uncle Bill, why there's a discrepancy there. Don't know. It's I think a shift of 7 or 8 angstroms. I think that's pretty significant. So, not quite sure what's going on there. I just might be completely wrong. We'd have to look that up, but I I think there is a little bit of variance there. I'm not exactly sure what that's caused by. Oh, just by the way, the reason why I know that is my favorite color is because for a time I had I had access to uh, a device called a spectrophotometer, and a spectrophotometer emits light at any wavelength that you choose. So if you want to calibrate an instrument, right, um, um, you can use a spectrophotometer to do that, because it'll emit at any wavelength of light. And it just so happens, I'm not exactly sure how or why, but we dialed into H beta, And when I saw that, it's just like, oh, yeah. So yeah, I've actually seen it, and it's great. It's really really great. Anyway, so you know, I look at these, especially these. I mean, this one, you know, okay, okay, if you point it out to me, I'm going to say, okay, there's some absorption there, right? These things go down, and there's bumps in the middle. And if I look around, it's sort of like, well, there's a lot of things like that. This is really, 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 at least to me, right? This is really, really close to the noise. And to be able to fit that and be able to, I don't know. I don't know. I mean, I'm not a spectroscopist. I don't claim to be one, but I do understand signal to noise, right? And to me, the signal to noise on this and this is very, very low. Now, I can probably guess that somewhere in this paper they have measured that. Let's just try. There's photometry. That's orbital motion. Oh, I'm not getting anywhere here. Because J 2215 becomes very faint around that, where the cold phase of the companion star dominates, corresponding isospectra have low signal to noise. Okay, well, I'm going to say, okay, yeah, I guess what they're calling, that's a capital Greek letter of some sort. Sorry. Um, well, maybe I'm not understanding what that means. But yeah, low signal to noise there. Let's see what else they say. Signal to noise. That's all they say. We average 4 to 6 source spectra. Yeah, they don't talk about the signal to noise of the spectra. Come on. I I want to say that this is some kind of measure of the signal to noise. And if that is, I don't know. That's really, oh, that's hard. That's a hard pill to swallow. Yeah, that's a hard pill to swallow. Yeah, see, here's magnesium 2, here's magnesium 1, and it's like, where? Okay, let's zoom in again on this. It's like, where are those absorption lines? Okay, here's H beta, right? There it is. And why can we see it? Because it's got good signal to noise, at least good enough, right? But where is the magnesium 1 here, right? Where's the magnesium 2, right? I mean, we know where they're supposed to be, right? But, oh, come on. I don't know. Let's see, what else have we got here? I wanted to show you some pictures that they made. Okay, yeah, I think this is just what we looking at a little while ago. But they made these really cool pictures here. There's the models. There's all that. So yeah, imagine, right? This third of a solar mass companion star careening around this neutron star every 4 hours, right? I mean, so I gotta say that's moving fast, right? But not only that, right? The neutron star is spinning at 1,000 times a second, right? And not only that, but the neutron star is so hot, and this companion star is so close that its neutron star facing side is like 2,500 degrees hotter than uh, than the other side. I don't know. It's just I'm not, and I would really like to understand this, but I I started looking at this, and I don't know what I'm seeing. It's some kind of correlation thing, some kind of a correlation uh, graph, but I don't know. I don't know. They're calling it a parameter distribution. So yeah, I'm not following that at all. But yeah, okay. So here's these things. So this is sort of stretching the imagination a little bit. They're going into their models, which is fine. Um, they are using data um, collected from their observations, so it's fine. It's fine, right? Um, and so this is what they think it sort of looks like. Um, these these colors they say are um, arbitrary flux units. So it's just where it's light, it's really really bright, and where it's dark, it's dark. And so the columns here are the orbital phase, right? So here's a phase of 0, which, as I said, is either when the companion. Well, I I think we can safely assume, right, that this is when the companion is on the other side of the neutron star from us, because we're seeing this heated up face, right? So then, as the companion star orbits the neutron star at a quarter of its phase, of course, the hot side is going to be on that side. That means that the neutron star is over to our left, right? So then, as the companion star goes between us and the neutron star, I don't think that this is eclipsing. I probably not. Probably not. Then it gets some kind of interesting um, brightening here. That's hard to understand a little bit. And then, of course, as it goes through the third quarter phase, of course, the other side looks lit up. So then they they do this at different wavelengths, right? This is sort of a G broadband. So this is sort of what we would see supposedly. This is at the wavelength of that magnesium 1 emission. So you can sort of see that it looks a little different, right? Looks a little different. It's sort of out of phase here, right? All the bright magnesium is sort of on the other side here, right? Sort of implying, I guess, that this, uh, well, yeah, I guess it's sort of I don't know what that's implying. I don't know. I have to think about this a little bit. You really do have to think hard about all of these things. Um, They do have some conclusions here, though. So they've identified for the first time absorption lines from both sides of the irradiated companion star to pulsar, blah, 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 blah. So the magnesium 1 triplets effectively trace the unheated dark side, while hydrogen traces the irradiated side. So yeah, I think it's very, very cool. I have a problem with those magnesium 1 lines, but okay, based on the information they have, this is what they concluded. So that's all right. So the cold side is like 5,600 degrees, and the hot side is about 8,000. So yeah, there's a difference, of like 2,400 degrees there. Pretty cool. Well, come on. Come on, I'm pressing the down arrow and nothing's happening. Everything else is working. Thank you. Come on. You're going everywhere except where I want you to go. Look at that. Look at that. Every single time I want to go to number 5, it freezes. Come on, machine. Okay. Let's see. By modeling jointly both RVCs, don't remember what RVCs is, and the light curves in the 3 bands while imposing temperature constraints. Okay, so yeah, they're just talking about a center of mass velocity, 412 kilometers per second. 412 kilometers per second. Okay. Yeah, and again, third of a solar mass for the companion, and 2.27 for the neutron star. But I gotta say, everybody's pretty excited, I guess, about this. The fact that they found a a, a neutron star, a pulsar that is now the most massive one that they've seen. And I look at that and go, that data is a little sketchy. It's a little sketchy. Um, Whether they've got something, I'm not sure. Yeah, it's hard. It's hard to tell exactly. Um, but yeah, it's interesting work. Interesting work, hard work. It's insane. It's insane what the amount of work that goes into these kinds of things. I mean, you got to be dedicated. You got to be seriously dedicated, or crazy, either one. All right. Well, I'm going to get out of here for this time around. So hope everybody enjoys, has a great evening, a great day tomorrow. Hit the thumbs up if you so desire. Share this around. I'm trying to find my core people, right? My core. I've got 98 subscribers now, so it's getting close to 100, and that's pretty interesting. Number of subscribers really doesn't mean much. I'm just sort of um, setting that so when I pass that, um, you know, we'll have a little treat. So yeah, all right. Well, I'm going to get out of here for now. Hope everybody, as I said, has a great evening and a great day tomorrow. Um, Enjoy yourself. Have fun. Um, uh, remain curious, right? This is a bizarre existence we find ourselves in, and it's pretty amazing though too, huh? Pretty amazing. So sit back, enjoy, relish in it, because it doesn't last, right? Nothing lasts at all. So enjoy it while you can. I try to. I try to all the time. And that's exactly what I'm going to do right now. I'm going to go back and watch some more Doctor Who. All right. It's over on Twitch for I don't know how long. Dr. Bill, did you say like the next 7 weeks, the next 7 months, the next 7 days? Don't remember. I mean, seven weeks, I guess, would make the most sense. Yeah. So yeah, but I'm really glad that I'm able to see some, at least, of the classic Doctor Who, because it's awesome. It's awesome. It's so imaginative, and the acting is good. The stories are good. I mean, everything about it is really well done. And so what? You don't have CGI, right? You don't have all these computer graphics and all that kind of stuff. But you've got real people, actual physical people who are acting, and they have, you know, whatever they're wearing or whatever else. I think it's great. I I think it's great. I don't think it's tacky. I don't think it's cheap. I don't think anything at all. I think it's awesome. I think it's very awesome. As I said, my thing is if the stories are really good and the acting is really good, I can ignore everything else. I don't care what they're wearing, right? Not necessarily. If it's contrary to the story, then it's like, okay, well, that makes sense. But, if things aren't quite shiny enough, or if they're not really able to do what they want to do because of, some kind of limitation, um, so what? So what? Just follow the story, right? All right, I'm going to get out of here. Peace, cheers. I will see you on the spin in a little less than 23 hours. All right, take care, everybody. Neutron Star Ho. Bye.